The UN has predicted that by 2050, 68% of the world's population are going to live in our cities. And with this comes significant challenges for the global construction industry. We're going to be required to meet the growing demand for urban housing while employing sustainable measures to ensure there is no further advancement of climate change and to help reduce our progressively increasing risk of our urban communities to natural disasters. So what is the solution to some of these challenges? Well, the solution actually appears quite easy. We just need to build more houses with low embodied carbon using sustainable materials on low-risk sites. But the real issue is what material allows us to do this. And traditional construction materials such as steel, reinforced concrete, brick, aren't necessarily always appropriate for use to solve these problems. For example, traditional construction materials tend to involve labour-intensive construction, which leads to long construction schedules, meaning that it's difficult to build housing quickly and cheaply. The production of these materials involves the use of non-renewable resources, further depleting our natural resources. To construct on low-risk sites tends to be expensive, and therefore we need a high rate of return to construct economically viable residential buildings. And traditional materials, with their long construction schedules and high labour requirements, tend to be fairly expensive and therefore not always necessarily appropriate for economically viable projects on high-cost sites. And finally, the production, transportation and construction methods associated with traditional materials, as we know, tends to emit high levels of greenhouse gases, which is further contributing to climate change and resulting in buildings with high embodied carbon. As a result of these issues, timber is regaining popularity as a construction material, and the new engineered wood product, Cross-Laminated timber, or CLT, has emerged as a competitive alternative to traditional construction materials for use in the construction of multi-storey residential buildings. For those of you who aren't familiar with what CLT is formed from layers of timber boards which are bonded to each other orthogonally to create large two-way spanning panels which can then be used to form walls, floors and roofs of buildings. So why is it that CLT is going to solve some of these problems? Well, CLT is a prefabricated material. It's brought to site ready to be installed, and this means that it's reducing on-site construction times and labour requirements. If the timber is sourced from sustainably managed forests, it's a sustainable material. While the cost of CLT is comparable to concrete, it has a higher strength to weight ratio, and this means that on sites where foundation loads are restricted, taller buildings can be constructed using CLT, meaning that there would be a higher rate of return and more likely to be an economically viable project. And finally, timber sequesters carbon. And not only this, but very low levels of greenhouse gases are emitted during the production of CLT, and it can even lead to carbon neutral or even carbon negative buildings. CLT buildings as tall as 10 stories have been constructed in areas of low seismicity. However, very few multi-storey CLT buildings have been constructed in areas of moderate to high seismicity, and this is because at present there are still no structural codes for the material, and the sort of understanding of the behaviour of components within multi-storey CLT buildings, such as wall systems and connections, is fairly limited. And so my research aims to add to the experimental basis necessary to inform design guidance for the construction of CLT, design and construction of CLT buildings under lateral loading. And this is to be undertaken by experimentally investigating the behaviour of CLT wall systems, which are representative of above ground floor story wall systems within a 10-story CLT building under monotonic lateral loading. as well as experimental investigation of the behaviour of typical above ground floor CLT connections under both monotonic and cyclic loading. So firstly, looking at my connection tests, my test program involved a total of 72 tests where I was testing multiple types of connection using different fastener arrangements under both monotonic and cyclic loading. But today I'm just going to focus on 2 connection types, and these are the 2 connection types which were then used within subsequent wall systems tests. And these are the Rotoblast WHT 340 hold down and the Simpson strong tie ABR 105R angle bracket. These connections were tested under both under monotonic loading and both shear and tension. And the images on the left there show the test setup for the tension test, and the images on the right show the setup for the shear test. In the tension test, the floor panel of the test specimen was restrained while the wall panel was pulled upwards. And for the shear test, the test specimen was rotated 90 degrees from the tension test position, and the wall panel was restrained while the floor panel was pulled upwards. From the graph on the left, we can see the results of the tension test. And as you can see, the hold down has greater tensile strength than the angle bracket. And from the graph on the right, we can see that the angle bracket has greater shear strength than the hold down. And this is expected because in the design of any CLT building, it's assumed that a hold down will resist overturning only of the walls, and an angle bracket will resist sliding of the walls. And therefore, hold downs are subjected to tensile forces only, and angle brackets are subjected to shear forces only. But as we can see from these 2 graphs, the angle bracket still has notable tensile strength, and the hold down still has notable shear strength. And therefore, it's more likely that within a CLT building, both of these connections are jointly contributing to the overturning and sliding resistance of the walls within the building. And therefore, all of these strengths should be considered for a more efficient design of connections within CLT buildings. Following the connection tests, I undertook a series of 10 tests on a CLT wall system. In the test, a vertical load was applied and maintained throughout each test, and each vertical load was representative of the typical gravity load that you would experience at various floors within a 10-story CLT building. As my work focuses on above ground floor stories, I didn't look at the gravity loads of the ground floor, nor did I look at the top floor, as the vertical load would have been quite low. So the vertical loads are representative of gravity loads at floors 2 to 9 of a 10-story CLT building. In test T1 to T8, the wall was loaded laterally to a maximum lateral load of 50 kilonewtons. And this was to ensure that the connections behaved elastically, and it allowed me to use one wall system to investigate the relationship between vertical load and global deformation of the wall within the elastic region. And following these 2 tests, the maximum lateral load of 150 kilonewtons was applied while a constant vertical load was maintained, allowing me to assess post-yield behaviour of the wall. This image shows the test setup. Both the wall panel and the floor panel had the same dimensions, and this allowed the wall panel to be placed centrally on the floor panel so that the floor panel could be fixed to the lab floor at all 4 corners. And the hold down and angle bracket connections were the same as I discussed earlier in relation to the connection tests. The displacements were measured at 19 locations within the wall system, and this was very extensive monitoring, and much more extensive than has been undertaken in any previous studies into the behaviour of CLT wall systems under lateral loading. So looking at the results of these tests, as the lateral load is applied to the wall experiences an overturning moment, and so there's an uplift of the wall. And the non-linear relationship between the uplift in the wall and the vertical load at the maximum lateral load of 50 kilonewtons is shown in the graph on the right. As the wall is lifting up, there is a lateral displacement at the top of the wall from the initial position, and the relationship between that lateral load at the top of the wall at the maximum lateral load of 50 kilonewtons, and the vertical load is shown on the graph here. As the wall is loaded laterally, it's undergoing a combination of different types of deformation or different deformation mechanisms, and these include in-plane deformation of the wall panel, as well as rocking and sliding of the wall. And therefore, the total lateral displacement at the top of the wall is due to a combination of all of these different deformation types. Because I measured my setup so extensively, I was able to determine the extent to which each deformation mechanism was contributing to that overall global behaviour. And I found, as found within similar previous studies, that there were negligible in-panel deformations. And so only rocking and sliding were occurring, with the displacements due to rocking and sliding shown in the graph, the lateral displacements due to rocking and sliding shown in the graph on the right. As you can see from this graph, the contribution of each deformation mechanism is changing with vertical load. And this would suggest that throughout each story within a multi-story CLT building, you would have varying global behaviour. As you can see, rocking is the predominant deformation mechanism in all tests, and sliding is minimal but begins to become significant at low vertical loads, particularly in test T8, which was when the lowest vertical load was applied. And this is significant because rocking walls are self-centering once a lateral load is removed. However, if the walls are to slide and the connections are to yield, you can potentially have a residual lateral displacement once your lateral load is removed. I'm not going to have time to discuss this graph in detail, so I'm just going to focus on the test T8 results in this graph. From the connection test, I found that the approximate yield load of the angle brackets was 11 kilonewtons. And if we were to consider that the shear resistance of this wall system was provided by angle brackets only, it wouldn't have been expected that under any of my tests T1 to T8 in which I applied a lateral load of 50 kilonewtons, that the angle brackets would have yielded, given that the combined shear capacity of the 8 angle brackets exceeded the shear force. However, I found after test 8 that I had a residual lateral displacement. And one of the possible causes of this residual lateral displacement is that the shear capacity within my wall system was actually lower than the shear capacity found within the connection test in which I tested the bracket under shear loading only. And that's because within the wall system, as I found in the connection test, the angle bracket also has tensile resistance. And so it's likely in the wall system contributing to that overturning resistance and therefore subject to tensile load as well. And so under bidirectional loading, and this bidirectional loading may lead to a reduced shear capacity of the angle bracket. So in conclusion, there was varying global behaviour noted under different vertical loads. Each deformation mechanism was contributing to a different extent. And this would suggest that you could expect variable behaviour throughout a multi-storey CLT building, confirming the need to consider connection design at each individual storey. Both the connections have shear and tensile strength, and therefore are both likely to be contributing to both sliding and overturning resistance of the wall system. As the angle bracket may be also resisting overturning, it's subject to bidirectional loading, which is potentially leading to reduced shear capacity. And this is significant at low vertical loads when sliding becomes significant, given that sliding is undesirable and should be limited. And therefore the shear capacity really needs to be understood to make sure that it is sufficient for the building. However, further work is needed to quantify to what extent there is a reduction in shear capacity of the angle brackets. And finally, just to reiterate why CLT is such a promising sustainable material, here is an image of a recently constructed CLT building called Blackdale Student Residence, is at the University of East Anglia. KLH, who were the CLT supplier and subcontractor for this project, stated that this project required the use of 1,970 trees, which they have estimated is equal to the number of trees required to produce the newspapers, magazines, and free literature available every 2 days on London transport. And yet this building is capable of housing 514 students and sequestering 935 tonnes of carbon.